if you remember, where we ended up is if you're going to do a SPI transaction, there's a certain way you need to go about it. So with all transactions, what you have to do is you have to assert the chip select line. So you bring the chip select line low. You write some data on the bus. You can keep writing data on the bus, but generally if you're doing one transaction, you write data on the bus. You make sure that that transaction is complete. And then you will always receive data from a SPI transaction. So if you want that data, you can read it. If not, you can just deassert the chip select line and you can go. I put these comments up here specifically because when you're writing for the get-go, because you can potentially throw data in that buffer faster than it can be sent out, you want to make sure that the transmit buffer is empty before you put new data in. So all this fun you're having with double data in the UART, imagine having the same amount of fun with the SPI. So to make things simple, just put a single packet in, hold until it's done, and then put another packet in once this transaction is complete. There are a couple crucial registers as with any peripheral that configures its operation. The main one you want for the USART is the control register. And the control register does a couple things. A couple of the parameters that you want. There is an auto CS parameter in there. That automatically toggles the chip select line for you. Some devices have this ability. I never use it because I want to manually control the chip select line. Different peripherals may want the chip select line asserted between multiple transactions, and so I want to manually do that. You have the two main parameters that we talked about, was clock phase and clock polarity. Remember, phase is whether you are looking at a leading or trailing edge, and polarity is whether the clock is idle high or idle low. A couple other parameters that you care about in here. Sync. If you do not have the sync bit set, then you are actually using a UART. Remember, it's the same peripheral. It can be in a synchronous mode. It can be in an asynchronous mode. If you don't set that sync bit, you are working with the UART and you're back on assignment 3. The final thing is that you can change the transmission order, and generally in a SPI transaction, it is most significant bit first. The default in your peripheral is least significant bit first, because I think that's how UART does it. So you need to make sure that this bit is set to do most significant bit first. These are set to be the proper phase and polarity that you want, and that the sync is enabled. You want to make sure that you're in a synchronous mode. The other register that you care about for the SPI is the frame register, and the frame governs that packet that goes out. And so when we were doing with the UART, we had to set start bits and stop bits and parity bits, and we don't have any of that when it comes to a SPI transaction. There is no stop bit, there is no start bit, there is no parity. Those properties of the peripheral should be ignored when it's in synchronous mode, but just to be safe, turn them off anyway. So say no stop bits, say no parity bit. Those features should be disabled, but go ahead and turn them off to make sure that they never happen. A default SPI transaction is 8 bits. I've never really seen one longer. There's no reason you couldn't have one longer. But when you set up the frame size, set it up for 8 bits, because that is the default SPI transaction size. Now, just like before, there is the command register. And it's sort of unfortunate that they call it this, because when you have the timer register and you have commands, you actually make the timer do stuff. You start it, you stop it, it's nice. Here, for the command register, you're enabling transmission and you're enabling reception. You're not actually causing those events to occur. You have to use the command register to enable being a master, to be enabled to transmit, to enable to receive, and then once you do those things, any data you place in the transmit buffer will automatically be sent out. So it's sort of confusing when you say, oh, command, I'm going to make it transmit. No, you're not. You're going to enable it to transmit, and then when you put data in the shift register, then it actually transmits. A couple people discovered that as they were going through assignment 3, they were being good students, they were writing their configuration data, and they came to me and they said, well, I can't see any of the bits that I've set in the command register. And you never will, because the command register is a write-only register. A write-only register means that when you read it, you read all zeros. So you will never see these bits actually set. So if you think you're writing to a register and it's not doing it, it's one of two things. Either one, the clock's not enabled for it, which means nothing happens, or two, it's a write-only register and you'll never see anything anyway. So that's configuring the peripheral itself. Those registers, command, control, and frame. Those are the main configurations for the SPI device itself. You still always have to configure the GPIO. So for assignment 3, you had to make it route 1. You had to use the route 1 pins. We used those because they were exposed on the headers. And you had to make certain pins inputs, certain pins outputs. Same thing happens here. The MISO line, which is master in, slave out, is how you receive data. So this pin needs to be made an input. MOSI, which is master out, slave in, needs to become an output pin. And the clock pin needs to become an output pin. So not only do you have to go and configure the pins as inputs or outputs, you also have to make sure that the route register is set so that the SPI functionality goes to the correct pins. You will also need to configure the chip select pin as an output, and we will do that manually, and you'll manually control the chip select. Questions on this? So, what I'm going to tell you though, is that setting up all of this and this is just sort of long and tedious. And in your lab, you have an initialization function, and I've broken that down into several smaller functions called configure clocks, so turn on the clocks you want. Configure SPI, which means set up the SPI to the values that you want. Configure GPIO, which means configure all the GPIO as proper inputs or outputs. You're going to want to break those things down because otherwise this is going to be like a 50-line initialization function, and I don't want you to get lost in what's going on. So use functions and break it apart to help segment the code in your mind. Here's the entire list of things from start to finish to get the SPI ready. All right? Configure all of your pins. Set the location in the route register. You then have to enable the pins in the route register. So all this does is set them as inputs or outputs and routes the functionality to those pins. This actually enables the functionality. This is configuring the SPI device itself. So you've got to set it in synchronous mode. You've got to configure the clock frequency. So remember that baud rate calculation that's in the slides. You've got to set the polarity. You've got to set the phase. You've got to set the packet structure. And then you've got to go into the command register and actually become a master and enable transmission and enable reception. This only configures the SPI device. It doesn't configure the accelerometer that you're going to talk to. So these are the 7, and it's actually a couple more embedded, the 7 steps that you need to configure your SPI to actually talk to something. And the reason that this is so complicated, the genius of Arduino is that they make this go SPI.begin, and it just does it. And the reason that people like it is because they've made a bunch of assumptions. They use the same chip family, they use the same pins, they set default frequencies, they set default parameters. So all these changes that you're kind of making, something like Arduino, libraries like that, just make the assumptions for you. It's not that the chip lacks the capability, it's just that someone says, these are the most common settings, and I'm going to default set them up for you. You can change them later, but these are the defaults. So all of this happens in like serial.begin or SPI.begin on Arduino. And the reason it's popular is because you don't have to know any of this crap to get it working. The trouble with something like Arduino or any other little processor like that is if it breaks, or if the device doesn't conform to the data sheet, or if someone on GitHub hasn't written you a library and you don't know how to write your own library. So the reason I teach you all these details is so that if you, A, are using a library like that and it breaks, you can fix it. Some of my embedded system students this summer and then last spring are using a graphics library, but it blows up on their processor. It blows up on their processor because the frame buffer is too big for the chip they're using. At the same time, you may be working for a company or a place that uses old TI chips that no one's ever used before, and they have the data sheet, and you've got to dig into the data sheet and figure out how all this stuff works. So, in every embedded system, every microprocessor you use, you may not have to go through all these steps, but at least you know how to go through all of them when you need to. With that, I'm going to jump over to the lab, and we're going to go through the configuration of how to set up the SPI and how to set up the accelerometer. And once we do that, you'll have sort of the rest of the lab to really get started on that. Any questions on this before I flip over to that? And I will upload this and put it up onto the lab. All right. What your lab is to take the SPI interface on this device and connect it to an accelerometer. And that is the entire point of having a microprocessor, is to connect it to some other device. And what you're going to connect it to is one of these 3-axis accelerometers. If you're in Capstone or you're doing anything with accelerometers, and you go to DigiKey and you Google accelerometers, there's 3 billion choices. They can be analog interfaces, they can have I2C interfaces, they can have SPI interfaces, and they're all like $5. You can have whatever choice of things you want. This is just a particular one that I picked from SPI. I also use things from analog devices, but what you have is a little accelerometer with a spark plug breakout board that solder header on. Not a big deal. There are lots of little things on this breakout board. You've got your SPI or I2C interface. It can do either. And it's also got on it an analog to digital converter, so it can take samples. And it also has a temperature sensor on it. Because why not? Because you've got extra functionality, you've got extra chip space. It does multiple things. But here's your little chip here, and all of the pins have been broken out for you. The labeling of the pins, because the resistors are in the way, is kind of wonky, but it's ground, VCC, and then this is called SDA, SDI, so that's serial data or serial data in. So this is MOSI, clock, MISO, and then your chip select. One really important thing about this part is that this is a 3.3 volt part. Your processor is a 3.3 volt processor, as you answered on lab 1. But there is also a 5 volt output on your breakout board. So we're going to use that. You connect to the power supply and move them up. That's the same right there, but I've got a diagram again showing you which one it is. This also has some interrupt pins on it because it's nice. Usually you just don't sit there and pull an accelerometer for hey data, hey data, hey data. You usually wait for something to happen and then an interrupt occurs and wakes you up. So on my Apple Watch, when I turn my wrist this way, it lights up. And it doesn't do that by sitting there going, hey, what's the orientation, over and over. This accelerometer waits until it's at a certain orientation and then triggers an interrupt. So that means the processor on here can go to sleep while it's not doing anything, especially the screen can go to sleep because the screen's a big energy hog. What you're going to do is you're going to take the SPI interface on the board and you're going to talk to this processor. You're going to talk to this chip. And all you're really going to do is initialize it, turn it on, and then get a single acceleration vector. And if you calculate the magnitude of that vector, it should be close to 1, which means it's sitting right here on the table. If you get more than one, then that means somehow you're accelerating your accelerometer, and you're either throwing it or there's a gravitational wave coming through. So you're going to have to configure it, and you're going to have to read your X, Y, and Z acceleration values. A thing that I learned in this lab is that you implement all of this in C++ class. So I have given you the skeleton for an LIS 3H class. So it's a C++ class. It has certain public and private methods. It's got certain member variables. And you'll see a lot on embedded systems that when someone, instead of writing just a bunch of individual functions for a device, they'll write a library so they can encapsulate all the gory details. And you're just going to kind of complete the rest of that class. When you're connecting this up, we are going to use SPI number 1. So if this is the top of your expansion header, this is when you're looking at the pins on the back. You've got MOSI, MISO, and clock. This is technically the chip select pin. We will use it as a manually configured GPIO. I guess technically you could use any GPIO that you want, but go ahead and use PD3 as your chip select. When you're connecting this up, this pin right here is ground, negative. This pin right here is 3.3 volts. The pin beside it is 5 volts. Use the 3.3 volt one. And the pin immediately below it is ground. So, where are you at your processor? So if I'm looking at this, all of your SPI connections are over here. This rightmost pin on the top is 3.3. Immediately below it is ground. Make sure you don't flip out on the ground and fry your chip. Here's what the internal guts of this look like. You've got your I2C or SPI interface, and then there are a bunch of control logic, and then there are 2 analog to digital converters. Why are there 2? They probably have extra chip space. They want to kind of give you extra value for your money. And it doesn't really cost them anything if they're already putting one ADC on here to measure acceleration. Put another on here and make you think that it's awesome because it gives you temperature and 3 analog extra inputs. As with the other SPI devices that we talked about, all of this configuration data here is memory mapped, meaning that you're going to have to write to the messages inside of this accelerometer to control it and make it do what you want. At boot, it goes into power down mode, so it does nothing. So you're going to have to wake it up, configure it, get it ready, and then pull data out of it. There are a ton of features on this device that we're just not going to use. One, because we don't need to, and 2, because the documentation is terrible. But we are going to set it up just to sample the X, Y, and Z axes at 50 hertz in high resolution mode. And I will warn you that this product has a bad data sheet. But I keep using it because it has a bad data sheet, because that's real life. So sometimes they will call this normal high resolution mode. Sometimes they will call it high resolution mode. We're in normal full powered mode with 12-bit resolution. That's what we're doing. And you're doing all 3 axes. Now, to configure all of the bits, to configure all of the values, you're going to need to read and write from the internal registers. So the slides that I showed you in the main lecture were the slides for this device here. And the way that you read from a register is that you put the address of the register on the bus, and then you send bogus data, so send a bunch of zeros, and then the data comes back. So you have to send extra data to generate this clock signal such that the slave can respond. And what this timing diagram shows you is the structure of the packets. So this bit here is the read-write bit. They call it bit 0. It's really like bit 7 in the real packet, but we'll just go with it. So if you want to read from a register, you are going to put a 1 here and then the address here. This MS bit is sort of a burst read bit. So if you want to read a range of registers, you would say, I'm going to start reading register A, and then every read transaction after that is going to go A, B, C, D, E, F, 1, 0, 1, 1, and so on. It's going to keep going through all of memory. If you were going to do a bunch of reads, a bunch of block reads, you could use this feature, but you don't need it. So don't even worry about this bit here. So read or write, and then the address. Again, make sure you send the dummy data and make sure the data is most significant bit first. Same thing with a write. Here, you're going to set a 0 because you want to write. I want to write to some address, some data. So what that means is you're going to have a function that transmits the address and then transmits the data. You're going to do it over and over, and that's how you're going to write to the device. So this is what you've got to do. When you've got the SPI configured, you're going to need to transfer some data over the SPI bus, and you need to figure out the structure of the packet that you want to write to. If you wanted to read from address F, this is the way the packet would look. So it's an active low write, so you have 1 here to read. You're not going to use the MS bit, and then in the address, you need to put F. So 1110, sorry, 1111 for F, and then 00. So you need to construct a packet, an 8-bit packet, transmit that packet on the bus. And then that will cause the accelerometer to look up the data in address F, and then when you send another dummy packet, it'll then produce the data onto the bus. In the same way, if you wanted to write to address 20, you put this low for a write, you don't use the MS bit, and then you write to 0 for 20 into this lower address. Questions on this? Questions on how to set up these two packets? So what you're going to have is you're going to have I'm going to give you a function called read register and write register, and it's going to pass an address. And so this will already be an 8-bit value, and you're going to need to do Boolean ORs or Boolean ANDs to set the bits that you want. Excuse me. To make sure that the packet is the right structure. So these are the two functions that I'm going to give you in the class. You're going to have a read register class. You're going to have a read register function, which just takes an address. You're going to have a write register function, which takes an address and a piece of data. These are going to be like your bread and butter functions. These are going to be great. Because all this configuration data we're going to have to set, you want to just say, write this value to this address, write this value to this address, and just kind of do it over and over. To implement these functions, you will also use the SPI transfer function. And so what SPI transfer does is it basically just puts data on the bus. And that's all it does. Just puts data on the bus, and there you go. So the way that read register will work is that you'll need to lower the chip select line, put data on the bus of the address, put dummy data on the bus to make the read occur, raise the chip select line, return the data that you get. All SPI transfer does is check to make sure that the transmit buffer is empty and then put data on the SPI bus. Your write register function is going to do the same thing. You're going to lower the chip select line, you're going to write the address, you're going to write the data, you're going to raise the line, and then you're going to return. You don't necessarily care about the result of a SPI write, so you're just going to return void. Questions on these three? Because these are the three most important functions that you're going to have in the lab, and you have to make sure that they're right, otherwise nothing else will work. It will be. Yeah, it will be once we're done. No, so you have to write it all down now. When you're doing the SPI transfer, you gotta make sure two things occur. One, don't put data in the transfer. Don't put data in don't leave the function, the transfer function, until the transaction is complete. Why? Because you can immediately throw some data in there, and you're going to back up your transmission log. So just as a safety thing, don't leave the function until you've completed your transaction. So the way that it sort of looks, or the way that the way your code is generally going to look is sit here and wait until it's empty, throw some data in the transmit buffer, sit here and wait until it's done, and then if you want any of the data, return it. Because on a SPI transaction, you're always going to have data. I emailed out to you yesterday a software guide for class. And that's meant to be sort of general practices and rules when writing good code. And one of them talks specifically about blocks of code like this. So a lot of times in code, you're going to be sitting there polling on some flag. And if you're using something like read bit, you're going to have a line of code that says like read bit uStart status 6 equals 0. You go, well, what the crap does that mean? Like, what is bit 6? What am I waiting for? So what I do in the code is I make a Boolean called transmission is done equals false. And I sit there and I poll on that flag. But inside the body of the while loop, I update that Boolean variable. So you could literally have a variable called transmission buffer not empty. And you can sit here, you can name your variable so that when you're polling on that data, you know what you're actually waiting for, what condition you want to occur, rather than waiting for bit 6 to not be 0. So if you'll notice, I'm basically giving you these functions, and you need to fill in the proper functionality. Please pay attention. Please pay attention to my comments, and please follow the comments as they're written, because that'll make sure you do the operations in the correct order. Okay. Remember that slide at the end of the previous lecture? I said there's 7 things that you got to do to get this thing working. We're going to walk through all 7 of these right now, and we're going to put them on the board, and you're going to have them, and we're going to figure out all the stuff that you need to do to get this SPI device ready. So it's all the stuff of configuring the GPIO, configuring the pins, and turning on the clocks, and all that fun stuff. So take a look at the reference manual. Go to the reference manual, and we're going to fill out this table. So if you want synchronous mode enabled, what bit do you set here? What field? What range? What I really want to be able to figure out these parameters here. Now I'll just give you these because we can go to the more complicated ones after this. So what we want to do is complete the table that says, to get in synchronous mode, I want to set a certain value in a certain register and calculate it out. And remember that there's an equation that governs how you calculate sort of the ball rate. So I've got 4 sets of tables, and I want each sort of row of table to figure out one of these. And so Kevin, you're by yourself. It's all right. You can do it. So you guys up here. This device needs to be in SPI mode 3. How do I make this? What value phase? This table here. This needs to be SPI mode 3. What's the polarity? Guys in the back. If I want to set up the packet to be 8 bits, no stop, no parity, what is the register that I set? What do I do? Kevin, if I want things to be in most significant bit order, what's the register? What's the register that I modify, and what values do I put in?
Full register?
Yeah. So just work on. We're all going to take a minute or two to work on this. But line 1, line 2, line 3, line 4, and we'll figure out what parameters need to go in here. So, yeah, figure out, first thing you got to figure out is control register. You got to figure out what register is in and what value you want. All right, let's take a look at these. Bin, clock face, what's the register? If I want to change the clock face, what's the register? All right, so it's the control register. What's the field name that I want to change? All right, clock phase. What value do I want to put in here? Okay. Matt, if I want to have an idle high, what's the register? Control. Okay. What's the name of the field? PLL. POL. What's the value? 1. Okay. Yes. What is the bit? What's the bit here?
Bit 8.
Yeah. Ben, what's the bit for this? If for the phase, what bit is that? 9. All right, Joe, if I want to have 8 bits, no stop, no parity, what's the register that controls that?
Frame.
Okay, and what value do I want to set in frame?
At bit 0, you want to write 5.
Okay.
Bit 8, you want to write 0.
Write zeros? Okay, so where's the one where I'm writing 5 to? What's the range there?
0 to 3.
Okay. And what's the name of that field?
Data bits.
Data bits. And I'm going to write 5 there, and the others I'm writing 0. All right, Kevin, if I want most significant bit first, what's the register that does that?
The control register.
Okay, what's the bit there? Give me the name. Give me the bit position number and the name of the field.
Okay, and it is,
Let's do this way. What's the value that I need to put in that field? 1 or 0?
here it is, number 10, SPI. And you put a 1.
Okay? So every line on here is some value that you're going to change. This does not necessarily mean that you're going to do 4 lines of code. Since you're making several modifications to the control register, I would read the control register, I would change all the bits that you want, and then write it back out. You can, if you choose, call modify bit field, modify bit field, modify bit field, modify bit field. That's fine. But if you know you're doing multiple operations on a single register, just read it once and then do all the binary operations that you need. So, did we get this right? Whole, that's the entire frame register, most significant 5511. Yep. That's like slide 1 of like So that's why I said we're going to sit here and we're going to do it all together. So you need this configuration here and all of these bits there. Okay? Now, you've got to configure you've got to enable all the properties, all the pins on the GPIO, and you've got to set the pin location. So, line 1, 2, 3, 4. We'll do it again. Actually, yeah, no, let's stick with that with this one. So line 1, 2, 3, 4. Kevin, you got the last line. So take a look at these, and if you want to enable the transmit pin, enable the receive pin, enable the clock pin, what's the register that you change? What's the field that you change? What's the value that you put in there? If you want to make the functionality go to location 1, what's the register you change? What's the value that you put in there? Can you read it? Okay. So I want to know if I want to set the pin location to location number 1. What do you do? I will tell you that all of these are in the same register. The route register deals with routing, the command register deals with functionality. We're talking about routing and configuration here. So take a look at one of those registers. Yeah, you're still within the SPI. You are still within the SPI device. What register are you in? And again, there's the route register, which deals with truly moving signals around. And there's the command register, which enables functionality. So TXN is transmit enables. It's also transmit pins enables. They should name them slightly differently, but they don't. All right, let's take a look at these. Nick, what's the if I want to enable the transmit pin, what's the register I'm in? All right, what's the name of the field? TXPEN. What bit position is that?
First one.
The number 1?
Yeah, sorry, yeah, the middle one.
Okay. What's the value?
1.
All right, Kira, if I want to enable the receive pin, what's the register? All right, we're going to see a pattern here. What's the field? And what's the bit position?
0.
And the value is 1, right? All right, Michael, what register am I in? Yeah, there we are. What's the name of the field?
COKPEN.
Okay, what's the bit position? And I put a 1 there. All right, Kevin, you have the hard one. If I want to set my functionality to pin location 1, what register am I in?
The route register.
Yep. What is the field that I'm modifying?
8 through 10.
What's the name of it?
Location.
Yep. And what value do I put in there?
1.
1. Okay? You don't need to enable the chip select pin because we're going to do it manually. We're going to do it manually with the GPIO calls. Every one of these slides is going to be like a function you should write called like setup pins, or you're going to put them in a block of stuff. Same thing. If you are doing all these modifications to the route register, you should just read the route register once, set bit, set bit, set bit, set bit, do whatever you want, and then write it back. There's no need to necessarily have a function call each time, but do what makes sense for you. Ben, yeah?
Does that mean you don't have to do this masking? You can just set the register equal to X value?
So, your if you have to do masking. If you know, if there's only like 5 things in this register, so yes, you can just straight write out the value to it. The masking is always good to do. Like, it's always good to do because it's going to be fine. But if you're super confident that, like, there's only 5 bits in here and you know what all their values should be, then yes, overwrite. But that's what I'm saying. So if you want to overwrite it, great. You might step on stuff. But if you want to do a modify bit field route 1, 1, modify bit field route 0, 1, like, be my guest. That's fine too. This is during sort of initialization. And so it's more important that it's clear and it's like super fast. So if you got extra function calls, fine. Okay? This is the difference though. These are changing up the pins. This is actually enabling transmission, reception, and being a master. This is separate things than what you've got to do. These are all in the command register: transmit enable, receive enable, master enable. Because this could be a SPI slave device. Maybe one processor is talking to another processor. So you need to tell the Gecko whether it is a master device or a slave device. Okay, that's just configuring. That doesn't put your GPIO in input or output mode. You still need to do that. You have to put them in the right input or output mode, but you should already have functions that kind of do that. That only configures your SPI device. You have to configure the accelerometer. There are 6 configuration registers in this accelerometer. They're called control 1 through 6. We are only going to deal with 2 of them, control 1 and control 4. So there's going to be a lot of bits that we set, but you're only going to ever set 2 registers. Control 1 governs how fast you sample, what power mode you're in, and which axes are enabled. So you can individually turn on and off different axes. Because maybe you don't need all 3 and you want to save power. Turning on an extra axis drains a little bit extra more current, and maybe you care about that, especially in a very low power operation. Control mode 4 also deals with the power mode, and it deals with the block data update. So the block data update is there's a FIFO on this device, and it's going to fill up as much data as you want, and you're supposed to read it in time with when it produces it. But we're not going to do that. So you need to use block data update to actually read whole data and not half of one sample and half of another. The documentation's pretty poor. Like I said, it contradicts itself, and also it's not the most clear, so you have to read the data sheet and you have to read the application note. Again, I make you do this not because I like to see you sweat or be punished. It's because this is what a real, this isn't some knockoff Chinese, someone made it in Minnesota device. This is done by SPI, which is a major company. And if they're going to produce bad data sheets, well, other people might produce bad data sheets as well. So documentation is terrible, but still, that's life. First thing you got to set is the device initially is in power down mode. That's the text in the data sheet. If you look here, none of this says power down mode. It says low power mode, but not power down mode. And you might think that's a little typo, but it gets really annoying when you're trying to figure out what it's actually doing. We need to set the device into high resolution mode. High resolution mode means that it's fully running, it's not asleep, and it's sampling at 12 bits rather than 10 bits. So to do that, you need to set certain bits in the control 1 and control 4 register. you need to set the low power bit off, and you need to set the high resolution bit on. So you'll have to put those configuration bits in control 1 and control 4 to put it in that mode. The control 1 register looks like this. There are 4 configuration bits, and then there's a bit that governs low power, and then there's bits that govern all the axes that need to be enabled. You want to turn on all of these axes. You want to set low power mode to 0, and then this ORD register is the one that governs the data rate. That sets the sampling rate. So we're going to need to set certain bits in it to be high resolution, and we're going to need to set certain bits in it to be at the 50 hertz that we want. Questions on this table? These two slides are not contradictory. Remember that this is talking about a specific bit in register 1, and that is a specific bit in register 4. So what I would do is I would say to myself, all right, here's the control 1 register. What bits do I need to set overall to make it do what I want? Well, I clearly want this, 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 not this, and now I need to figure out what these 4 bits are. And so when you boot up, once you've got your SPI working, manually calculate what you want the configuration to be, and then boom, write it out to this control register. The ORD bits are governed by this table here. And what it's showing you, it's a really bad table. What it's showing you is just basically the different configuration rates, different sampling rates that you can sample at. We want 50 hertz. And at 50 hertz, we want to set these values to be 0, 1, 0, 0. And what this is saying is this will sample at 50 hertz in high resolution normal or low power mode. These bits only govern sample rate. The other bits that we talked about here and here govern whether you're in low power mode or not, and govern whether you're in high resolution mode or not. So the way that you want to read this is you want to say, all right, if I want 50 hertz, then boom, my ORD bits are going to be these, and to get in high resolution, and in normal mode, you turn off low power and you turn on high resolution. It looks like you're formulating a question. That's not all we've got to do. Here is the high resolution bit that we talked about. We saw that on an earlier slide. The last thing that you've got to turn on is the block update functionality. By default, it's continually updating the output registers. So every time it gets a new sample, it just throws it in there. And at 50 hertz a second, it's not necessarily guaranteed that you're going to get a full sample. Like you might get half or one sample on the upper 4 bits, and then a different sample on the lower 8 bits. So to make sure that you have a good read, you need to turn on block data update. So after you've configured the SPI, all that stuff we went through on the tables, you now need to turn this thing into high power mode, high resolution mode, not low power, block data update, 50 hertz. That's what you need to configure it at. How the heck do you know if you're writing to this device and anything works? It's really hard to know because a lot of the registers are initialized to 0. So in most devices, there's going to be some special register that has a magic number in it. It's going to be a device ID, it's going to be a serial number, it's going to be something like that. You want to test whether your read function is working by reading out that special register. So there's a special register in this device called Who Am I? It's a very existential question, and if you're watching Westworld, it's even better. So, you want to try out your read register function on this address. And if you get back the number 33, then you know your read function works. Then if you know your read function works, try your write function, write to an arbitrary register, and then read it back. And if you get that value back, then you're pretty confident your write function works. So if your read function works and your write function works, then you shouldn't have technical issues writing to the device. You'll just have configuration issues writing to the device. I give as a bonus to the lab anyone who explains that joke. I'll 5 points in the lab. There are a lot of bonuses actually on this lab. So to test out your read register function, try to read the who am I register, and you should get back hex 33. Don't give away credit, Travis.
I appreciate it.
Now, last final bit of this. Your acceleration values are stored in memory mapped registers. They're all lined up. You need to then read out these registers 8 bits at a time. So here's the lower 8 bits of your x-axis, the upper 8 bits of your x-axis. So what you have to do is your x-axis reading is this high byte concatenated with this low byte. And you need to stitch them together to make a full 12 or a full 16-bit value. It is represented in 16-bit 2's complement, which really shouldn't concern you. You don't have to do the math. You just need to make sure that when you read this byte and you read this byte and you stitch them together, you make this variable a signed 16-bit value, and it'll magically do it for you. So just take this high byte, put it here, take this low byte, put it here, and make this an int 16t. Make it a signed value. You shouldn't be doing any sort of calculation to take those bytes and turn them into numbers. You just need to put the bits in the right position. So to get that data out, you're going to do 2 SPI transfers. You're going to get the lower byte, you're going to get the upper byte, and then you're going to concatenate them to make a full 16-bit signed value. And it is a signed value. And be careful when you shift your bits to make sure that you don't shift them out of range. Use bitwise operations for this. Use Boolean operations for this. Don't use add or multiply or divide. This should be bitwise operations. Even more. Your accelerometer is connected to an analog to digital converter. And an analog to digital converter is a magical device that takes a voltage and turns it into a number. What they've done is they've mapped the input range or the output range of that ADC converter. So the maximum value the converter can make is 2 to the 16, and the smallest value it can make is negative 2 to the 16. And that maps between 2Gs and negative 2Gs. So if you get the value 0 from your accelerometer, that means you have 0 Gs. If you get the number 32,767 from your accelerometer, that means on that axis it was experiencing 2 Gs. If you get negative 32,767, that means you experience negative 2 Gs. So the acceleration that this device experiences is encoded as an integer. That integer represents a physical quantity. So if you got a number in here, let's say you got 16,000, that would roughly correspond to 1 G. If you got negative 16,000, that would roughly correspond to negative 1 G on that axis. And the way that you're going to validate that this lab works is you're going to measure all 3 axes, and you're going to calculate the magnitude of that vector, and it's going to be really close to 1. Like, you should only be off by like 5%. And you're off because of calculation and because we're going to be using square root functions. This doesn't really support, but it's fine. But you should be really close, about 5% from 1G. Questions on this? We will talk more about ADC converters later, but they're really simple. They take a voltage, they turn it into a number. The higher the number, the higher the voltage generally. The lower the number, the lower the voltage. That's roughly how they work. So 32,000 is 2 Gs, negative 32,000 is negative 2 Gs. It's a linear scale. It's a linear scale between that mapping. Here's another bonus. This is table 9 in the data sheet. And this table basically tries to show you what I just said. So if you measure the value 5,600, that's roughly 350 millig's. Because if 16,000 is 2 Gs, then 5,000 is then only 350 millig's. At the same time, if you measure a 0 coming out, then that's 0 Gs. And again, if you measure 16,000 or negative 16,000, it's roughly negative 1 G, and positive 16,000 is roughly 1 G as well. This table is wrong. This table is wrong because the authors did stupid stuff with 2's complement. It's only wrong by 2%, but it's enough that it's annoying. And I'll give bonus if you can figure out what dumb things they did with 2's complement. This is real math, and this is the real rules that the device follows. This table is a terrible job someone did to try to implement those rules. And it's off. It's subtly off. But once you figure it out, you go, wow, that's lazy. So, that's a ton of stuff. That's a ton of stuff. This lab's got a lot of things in it. You've got to set up GPIO, you've got to set up SPI, you've got to talk to the SPI device. It's a lot of stuff going on. You need to turn on the SPI, configure the accelerometer, read the data back out. I have set up a main function that does it for you. All you have to do is implement the class. The main will call the functions in the class. The functions in the class will return the right values. Implement the missing functionality to complete main. I have left other functions in there as bonuses if people so desire it. Use the GPIO functions that you've come up with, or use the built-in ones to configure, like the chip select pin. It saves time. Or to configure things as inputs and outputs. I really don't care how you configure the GPIO. Just get it right. I give you the Arduino library that comes with this. So there's an Arduino library that's written for that. It will not help you configure your SPI device, but it will help you talk to the chip. If you're smart enough to read the library, figure it out, and implement it, do it. That's fine. Read the library, read someone else's code. Don't copy it, and you're not going to be able to copy it because it's a different framework. But if you can read that library and understand how Arduino talks to the SPI device, we'll bring that knowledge into your project and use it. I'm fine with that. As long as you learn and figure out how to talk to it, that's good. So, here's all your bonuses. 5 points if you explain the who am I joke. 5 points if you explain why table 9 is wrong. 15 points if you use timers and interrupts to read from the accelerometer. So if you set the timer to go off 50 times a second and read from the accelerometer, then you can do it. So don't pull on the SPI transfer, but use a timer and interrupts to perpetually read from the accelerometer. There is double tap detection on the accelerometer, so it can automatically detect when you hit it twice. So if you want to double tap the accelerometer, trigger a GPIO interrupt on your Gecko, and then turn on the light, great. I'll give you 15 points for that too. So I had a couple students do that last year. I had one student do that last year. Depends on if you need the bonuses, depends on how much you want to learn about SPI and GPIO. I think I have the deadline set for this as next Wednesday, and I'm going to push it back to at least next Friday. I want to make sure though that we don't run into too much against the exam, so I might move things around. Depending on how far people are. We're still going to cover the same material, but maybe we knock back the exam one day or so. Just depending on how much we get through on this. This is a big lab. This one's going to take a while. I don't think it's hard in the sense that it's technically challenging, but you got a lot of stuff to configure, and you need to be very methodical when you do it. So all that table, all that configuration, I I gave you that, and you need to do it that way. All this configuration stuff in here, you need to set it up, and you need to kind of do it in a good order. What I've given you for code, let me show you what this looks like. What I've given you for code is this. So there's a main function where I instantiate an instance of the accelerometer. So this is just the accelerometer class. I do it statically because this isn't a desktop and there's no such thing as new. New doesn't exist in microprocessors or embedded systems. It's bad. So just we make a static instance of this variable. What the main function does, and I've commented this out because yours won't do it yet, there is an initialize function. And initialize does all of the configuration. It configures the SPI, it configures the accelerometer, gets it ready to operate. Then it performs a self-test. And a self-test is reading that who am I register and getting the value back. Once it's done the self-test, it's going to get as floating points x, y, and z acceleration. So you should be able to look at these and see, well, this, if I'm in this configuration, this is roughly 0, this is roughly 0, this should be roughly 1 as the values you get back. It's going to calculate the magnitude of that vector. The magnitude of that vector should roughly be 1. You should be within 5% of 1g. What I've given you over here is sort of a sample definition of a register, and I've given you a class with sort of kind of way more stuff in it than you need to, but you don't have to use it. So there's the initialize function, self-test, get x, y, and z acceleration, and if you want bonuses, you can enable power down and disable power down mode if you still want to do that as well. There are some variables in here that are bus speed and pin location and scale range. I set those up for you, but this is just showing how you would do it if you wanted to make this class general. So if you wanted to pass it parameters of a different bus speed, a different sample rate, you would store these items. You would store these items inside the class. Your read register function, your write register function, your SPI transfer function, and then I've given you these functions here to help segment all that configuration information. So set up the clocks and turn on all the internal clocks you need. Set up the GPIO. Set up the USART itself. Whatever else you might need. Set up the accelerometer itself. There's also a delay function. Where is this? It takes 5 milliseconds after the device turns on to enter power down mode. It's unlikely that you will be talking to it 5 seconds after you power it up, but we're going to model those delays in the code just to be safe. Also, once you switch it over into high resolution mode, it's supposed to take 7 milliseconds to switch over. Your code's not going to be running that fast, probably, because you'll have breakpoints and you'll be waiting, but we're still going to put those delays in the code. Here is your C++ file. I've created a constructor. You don't need to do anything there. Whenever you are talking to the SPI device, just talk to this USART pointer. I have already set it up to be USART number 1, so you don't have to model. You don't have to change that pointer. But here's your initialize function. I suggest you implement setup clocks, setup GPIO, setup USART. I suggest you implement setup LS for the register. The self-test should automatically check against the who am I register and return true if correct, return true, or return false if you don't get the right value. This is a bad delay function, but it's close enough. So it should delay a certain number of milliseconds. You need to implement the read register function, the write register function, the SPI transfer function. You have to implement those. You have to implement you have to implement the get X, Y, and Z acceleration functions, and you really want to implement, I have it here, this convert reading to Excel function. So it's going to take that 16-bit reading and convert it into an acceleration. So you need to fill in the remaining functionality such that main works. So you can modify main if you want to try out different stuff, but I'm going to run your code. I'm going to take only your header file and your CPP file and run it against my main. So the main is going to stay the same, but your header, your class should work on sort of any main file. All right, a couple final points. Chips are up here. Chips are up here. A lot of them have headers on them. If they don't have headers, then you get the joy of soldering in headers. So if you like that, then you can wait. Or I think we have, how many do we have? 4, 8, 13, 11. So 2 of you are going to have to do some soldering. And I'll just kind of pick it as 2 hours so they do at least a good job. But we've got plenty of accelerometers. We got plenty of headers in there. So just stop in the back. Here, the 3 of y'all. This whole row is solid. Yeah. There you go. They're here. You don't have to stick these in a breadboard. You can just put the wires directly in here. I have a box of male, female jumper wires. Please put them back in this box, because this box is like male wires, and it just gets confusing when things are on the wrong side. So use these wires, wire directly from your gecko to the accelerometer. This should be more wire than anyone needs, but if you do need more wire, I will get some. It's a long lab. Spend some time on it today. Spend a lot of time on it over the next week. Email me, talk with me, and then I'll take a look and see what I have the deadline of right now. But I'm going to give you over a week to do this. So I think at least until next Friday, we'll get this done. So go ahead, get on it. Talk to me about it.